8 2024, question 54. Consider the process in the figure for manufacturing B. So let's look at the diagram here. So this is the feed which is coming in. In the feed contains 90 mole percent of A and 10 mole percent of inert. This is mixing with the recycle stream and then is going into the reactor. In the reactor, there is a reaction occurring to A going to B. And this says the single plus conversion of A in the reactor is 50%. So XA is equal to 0.5. Now, from here, reactor, it goes to a separator. Let's say it could be a distillation column. And from the bottom, it's coming out pure B, XB. So from here, from the output of the reactor, there'd be unreacted A, and then of course B as a product and the inner which is coming in from here. So this would be the components in this stream coming out of the reactor, out of which all the B will go in this stream, and this is pure B. And here it is xb is equal to 0. That means there is no B which is going in the purge stream. Now, since this is a splitting stream, so here the composition of N stream must be the same as the composition of P stream must be the same as the composition of R stream. Since there is no B in the purge stream, that means there is no B in the stream coming out from the separator, and there is no B in the reactor. Okay, what could be an example of this one? Just to find a similar example, not exactly the same. Let's say this the syngas of nitrogen plus hydrogen is coming in from here, and there'll be some amount of inert, which is usually argon, which comes over here to the reactor. And here, the reaction, this is happening. This is not exactly the same as this one here, but here, as you can see, this is 4:2, which is basically 2:1 ratio from here. And from here, this is entering the separator of just this ammonia is separated by condensation here. And of course, nitrogen, hydrogen, and the inert argon coming out from the top. And there's constant installed, so from this stream coming out from the separator, so that there is no buildup of the inert gas stream in this entire system. Okay, so this is coming back here. So now let us solve the problem. Let's assume the basis is equal to 1 hour. Remember that, let's call this one as F. This one is of K stream. This one is the L stream. This one is M stream. And this is N stream. And this is P as a bar stream, R as a recycle stream. Now, since this is a splitter, so the whatever the composition of N must be the composition is equal to the composition of P is the same as the composition of R. Okay. So on the basis of 1 hour, we can say the moles of B in this stream is equal to 100, because that's what is given. It's a pure B. Now this B must have come from here, from the reactor outlet stream. So the amount of B in this stream is 100 kilomole. So 100, now from the reaction stoichiometry, we can say for producing 100 kilomole of B, 200 kilomole of A must have been consumed. So consumed is 200 kilomole of A. Now, since there's a 50% conversion, which is given right here, so the amount of A which is entering must be equal to 400 kilomole. So 400 kilomole of A plus, of course, the inert which is coming in. Out of that, 200 kilomoles of A is converted to produce 100 kilomoles of B, and rest 200 kilomoles of A remains unreacted. So in this stream, we have A 200 kilomole, B 100 kilomole, and inert we don't know, but that is coming almost is exactly the same fluid as this one right here. And as you can see, the A and I are close boiling. So if it's a distillation column, A and I comes out from the top. Now here, so if this 200 kilomole of A, so that must be going over here in the N. So we have written this is the number of moles of A in the N stream is 200 kilomole. Okay. Now if we make a balance of A, so component A balance, so NXAN, N is the molar flow rate of total molar flow rate of this N stream multiplied by the mole fraction of A in the N stream. That means the total molar flow rate of A in the N stream, which is equal to 200 kilomole, we know. That must be equal to the moles of A in the P stream and the moles of A in the R stream, which is PXAP plus RXAR. Now, we know it's given R over P, the flow rate of the recycle to the purge ratio is equal to 10. And also we know XAN, that means the mole fraction of A in the N stream is equal to the mole fraction of A in the P stream is equal to the mole fraction of A in the recycle stream, and same is true for the inert also. Okay, so this XAP is equal to XAR. If we take that common, we can write this one as 11 PXAP. So PXAP is equal to 200 over 11. So this is the total flow rate of A in the P stream or the purge stream. So flow rate of A in the purge stream is equal to 200 divided by 11. So this is my answer.